In this video we are going to do a full structure refinement of this hydroxyapatite dataset. You will find a link to the file in the description below, so you can download it and try to reproduce what I'm doing here. We are also going to make heavy use of some of the features I presented in previous tutorials, namely the electron density maps and bimodal crystallite size distribution. This is going to be a lengthy video because structure refinement is a trial and error process, but it is a typical example of how I go about processing such a dataset when I'm interested in the refined structural parameters. The signal quality of this dataset is a lot better than what I normally use. The intensity is about 10 times higher than normal, and the angular range goes up to much higher values, 120 degrees in this case, as opposed to the 60 degrees I normally use. This is because we are going to squeeze a lot more data out of it, and you should only attempt such a detailed structure refinement with excellent data quality. First we have to create a refinement project and identify all the phases in our dataset. I already mentioned that it contains apatite. Hydroxyapatite reference phase should match fairly well, and indeed it's a little bit shifted to the left as compared to the reference lines, but it seems to be some kind of apatite. So I will create a refinement project with hydroxyapatite using my RMS-D8 ADS 15mm instrument as always, and run the refinement. And the first thing I check is it actually hydroxyapatite, and it looks like that was a correct choice. All the HA peaks seem to line up very well with the measured peaks, but I also see that there are additional peaks here, and probably this one as well. So there seems to be another phase, and the typical contamination in apatite is tricalcium phosphate, called TCP. But probably not the alpha phase. This one doesn't match very well. The beta phase looks like a better match. Again, the reference peaks are a little bit right of the measured ones. So it seems like all the peaks we measured are shifted a little bit to the left, but it worked with hydroxyapatite, so I hope it also works with beta TCP. So I will add TCP. It's already pre-selected, okay, and I repeat the refinement again, and it should move right here, and indeed it seems to find the correct peaks. So now we identified all the phases. There's no third phase in this sample. But we can see that there's still a problem with the peak shape. If we zoom into the strongest peak, our calculated peaks, the green ones, are wider than the measured ones. So we should do something about the peak shape refinement, and I will have a look at the hydroxyapatite structure file. We already refine crystallite size related peak broadening anisotropically. There's nothing we can do more than that, but I see that the K2 parameter, which refines peak broadening from a microstrain, is not refined. It's fixed at 0, so we can try and refine K2 isotropically. I also want to reduce texture to 0, so I don't want to refine preferred orientation in both of the structures, because these texture would correlate strongly with the structural parameters I want to refine later on. So we might have to activate texture again towards the end of the refinement, but first I want to try without texture. So now we just activated K2 and fixed preferred orientation. That's a lot better. The difference curve is flatter than in the previous cycle. If we zoom in, there is still a problem with the feet of the peaks. Apparently there is a fine fraction. Maybe the sample was overmilled when I prepared it. So we will address this in a minute. First I want to make some other adjustments. I want to change the starting values of the cell parameters A and Z, because now we know that the true values, the refined values from our list file. And the refinement always starts a little bit shifted to the right, and it takes a few cycles to find the correct position. So I want to use the refined values. I replace the ones in the structure file with the ones from my list file. And I do this for both phases, for beta TCP as well. So now when we start the refinement, it will immediately start at the centered position of the peaks, and it will find the solution much quicker. This saves some time and avoids that at the beginning the parameters go wild until it found the center of the peaks. So now let's address the issue with the white feet. If it's really a fine fraction, all we have to do is add the text block for bimodal crystallite size refinement. I introduced this in one of the previous tutorials. So we go to the text blocks menu and add bimodal crystallite size, and we start the refinement again. That looks a bit better. We will leave it at that for now and start with the structure refinement. We can see here that there are some intensity mismatches, and this is exactly what we will try to improve now with refining structural parameters. So first of all, I want to create an electron density map and see maybe I can figure out where these mismatches in intensity come from. So as I showed in the previous tutorial, to create the electron density map, I have to add a few output files, the res out and the FCF out, so for apatite. So I right click on the apatite structure entry and select add res out and FCF out files. This will create the output instructions, and then I run the refinement. There will be no change in the refinement strategy, but it will create the output files at the end of the refinement. Now I go to the Tools menu, select Electron Density Map to open the dialog, and I can open this FCF file, and it will compute the map. We want to use the difference Fourier map, so make sure the synthesis is set to fops minus fcalc. And now when I scroll through the unit cell, I am looking for high or low, so for excess electron density or for holes in electron density. And I can already see at the Ca2 position, the calcium atom, I have some excess in the observed pattern. So my structure model does not contain enough electrons at the Ca2 position. And here in the corner, I can see a blue hole. That's the O4 position, so apparently my structure model contains too many electrons at this position. And that's again the Ca2 atom. So these seem to be the most obvious discrepancies between the measured and the structure model. So let's address the Ca2 position first. We need more electrons at this position, that's calcium 2. It's fully occupied. The site occupancy factor is given in parentheses after the element. If there is no parenthesis, it means it's fully occupied, and this is equivalent to an occupancy factor of 1. So this would be equivalent to this. So how can I add more electrons to an already fully occupied site? Well, I cannot add more than 1 calcium there. I could add vacancies, so if I had too many electrons, I could just reduce the site occupancy factor, but I cannot increase it beyond 1. But what I can do instead is there might be a heavier atom. Instead of calcium, some of the calcium might be substituted with a heavier atom. And in fact, in this case, it is a strontium substituted apatite, so there must be some strontium on the calcium 2 side. Strontium is a lot heavier than calcium, but I don't know how much. So if we assume a 50-50 ratio, I could add code like this. So calcium would be 0.5 and strontium 0.5 as well, and it's all encapsulated in parentheses. So this would be a hard-coded 50-50 ratio of calcium and strontium. But we don't know the actual ratio, so we would like to refine it. And for that, we have to introduce a new parameter. We can call it, for example, P. So calcium, P is the calcium content, and 1 minus P would be the strontium content. So it's always fully occupied, but the ratio of calcium and strontium is refined. And to actually refine P, we add it here, param equals P, and we allow it to vary. So we start with a fully calcium occupation, and we vary it between 1 and 0. So now P is variable between 1 and 0, and we can run the refinement. We go to the electron density map dialog, but before I update the map with the new electron densities, I want to keep track of the range value. So now with the first iteration, we had a maximum excess of electrons of 1.35. So the range was from minus to plus 1.35. And as we improve our refinement, the range should get smaller and smaller. So the discrepancies between the measured and the modeled data or structure should get smaller and smaller. So now we want to update, to recalculate the electron density maps and to render the frames. And it's gone down to 1.2, so that was an improvement. And we don't see that much change at the calcium 2 position. Actually, the maximum of electrons is a little bit to the upper right, so it's not exactly at the center. There might also be a position mismatch. So we should not only refine the strontium content, but probably also the coordinates, the position of calcium. And other than that, we still have the hole here at the O4 position. And now we see that there's also an excess of electrons on the calcium 1 position. So there might also be strontium on position calcium 1. So let's apply these changes. To refine the strontium content on calcium 1, we just copy what we did on the calcium 2 position. We can use the same name for this parameter P, because the scope of this variable is only within this element definition. As long as we define it in the element line, we can always use the same name because it will not be known by the other element lines. So we can use exactly the same code to refine strontium on calcium 1 position. And we also wanted to refine the position of calcium 2. This is a special position with a Wyckoff symmetry H. So Z is given by the site symmetry, but X and Y can be refined. So we release both of them. And we can also refine the position of calcium 1. It's another special position. X and Y are given by the side symmetry, but Z coordinate can be refined. So now we are refining the strontium content and the location of both calcium positions. Let's regenerate the map. Now it's actually worse than it was before. The range is larger than what we had before. And there's not that much improvement on the calcium 2 and neither on the calcium 1 side. So maybe if we look at it from another direction, now we see this blue hole at the O4 position much better. That's actually the OH group in the structure. O4 is the oxygen of the OH group. And we also can see the position mismatch of calcium 2. So let's have a look at the results of the refinement. First of all, the strontium content on calcium 1 was about 5%, 95% calcium, 5% strontium, and on calcium 2 it's about 10% strontium, 90% calcium. The new coordinates, this is the Z, the new Z coordinate, and XY coordinates here. Now one thing we have to keep in mind is if there is substitutions on one specific site, it's probably a bit blurred. The position is probably not defined as well as if it was a pure position without any substitutions. So we might have to refine the thermal displacement parameter to take this blurring of different ions on the same site into account. So we can refine the TDS parameter, the thermal displacement parameter of both calcium atoms. First of all, let's start with isotropic refinement. Anisotropic is fairly sensitive, so whenever it's sufficient to use isotropic refinement, we should stick with it. And I also see that the O4, that's the oxygen of the OH group, has a wrong thermal displacement parameters. It was not given in the structure model in the template, but we should give some value. It's certainly not 0. It's probably blurred quite a bit because this OH group is also rather flexible. Let's try this. It's certainly better than 0, and we might even refine it. We also had too many electrons on this position. That's why it was blue in the map. So we should reduce the site occupancy factor. But we have to reduce the factors of both the O and the H because it's a molecule. So they have to change in the same way. But now we cannot just call this P and refine P here in this line because the second atom would not know about this variable. That's what I explained before, why we can use the same name because they are only known within this line. So if we want to use the same parameter for two different elements, we have to declare it outside. For example, up here, and I can call it site occupancy factor OH, and we start with 0.5, and we'll allow it to go down to 0, and maximum, well, we can set it to 1 and see what happens. And now we, instead of a number, we use this parameter here and repeat the refinement. So let's look at the list file first. The site occupancy of the OH group is 0.416, And so in the model it was 0.5, so indeed it is a little bit lower than what we used in the starting model. Now the strontium content is a lot higher. Now we have 16% on calcium 2 and 13% on calcium 1. Let's regenerate the electron density map. So now we already see a massive improvement of the range. It's gone down to 0.6. And the next mismatch is we have a little position mismatch on the O3 side. This might be the phosphorus atom, maybe. So it's mostly the O3 position and the phosphorus atom, so we can refine the positions of both. P is a special position, we cannot refine Z, but X and Y we can. So let's have a look at the map. We see a slight improvement in the range. And the mismatch in the phosphorus position is gone. And O3 still a little bit. So all the maxima we see are related to O3 somehow. Let's look at it from the other side. There is something wrong with the O3 coordinates, with the position, but we are already refining them. So maybe we have to refine the thermal displacement parameter. Maybe the position is more smeared. It's always a bit critical to refine thermal displacement parameters of light atoms such as oxygen. The signal is relatively weak compared to calcium or even certainly strontium. And also phosphorus is better defined usually. But if it's necessary, and we have very good data quality, so we can give it a try. And maybe let's also refine the one of phosphorus. The more parameters we refine, the slower it gets. So now on my computer, this already takes 2.5 minutes. Let's have a look at the map. Again, incremental improvement of the range. And we still see the same issue with the O3 position. I'm not quite sure how to fix this right now. Now we see some blue areas showing up around the O2. So we might just cut this short and refine the positions of all oxygens as well. Then we have pretty much all atomic positions refined. These are special positions, so we cannot refine the Z parameter. And also the atomic displacement parameters. And We can also, just to show how we would do it, it doesn't seem to be necessary, but if we want to refine the Z coordinate of the OH group, we cannot just refine Z of O and Z of H, because this is a fixed bond length. So we should not change the distance between the two. So what we can do is we can refine an offset parameter, so by how much these two atoms are displaced, and use the same offset parameter for both the O and the hydrogen atoms. And because we want to use the parameter for two different elemental sites, we have to define it outside of the element lines. And we call it delta Z ZOH. And we start at 0. And we have to define a lower limit minus, let's say, 0.1 and upper limit 0.1. And now we just add this to these two Z coordinates. So they will be displaced by this, from their given positions on Z, they will be displaced by the same amount, so the distance remains unchanged. And this is the hard-coded TDS we just assumed to be 0.02, so we can refine it and see if we get a stable refinement. So now we are refining all structural parameters, all the coordinates we are allowed to refine, all the TDS, the site occupancy factors of the calcium atoms and of the OH group. We cannot refine a TDS of hydrogen because this can only be done in single crystal or synchrotron data, but on a lab instrument we don't see the H atom. It's only one electron. So we will just leave it at the published value. I have one last suggestion to change the refinements here. I want to try anisotropic refinement of the TDS of the calcium atoms. Again, the rationale is that it's co-occupied by calcium and strontium. And in the last cycle we had how much strontium? 12% on calcium 2 and 8.65% on calcium 1. So these are significant amounts, and which means that this position is a bit disturbed and blurred because there's a smaller atom and a larger atom taking the same position, and we might get better results with anisotropic displacement parameters. But again, this only makes sense or only results in a stable refinement if we have really excellent data quality. Not much of an improvement, so they don't seem to be really anisotropic. And I think that's about all we can do. I have no idea what to change. And all in all, the map looks pretty okay. So the range is low, 0.5. Even though we can still see some. We might change the TDS, the vibration displacement parameter of O3 to anisotropic, but I would normally not recommend that. Maybe you should just stop at this point, but we can still try. No improvement whatsoever, so I guess this is our final solution. We have 12% strontium on Ca2 and 7.5% on Ca1. And down here in the refinement, in the refined parameters, in the local goals, we should see the chemical formula. This is the refined chemical composition with the strontium content. Now, as a last step, we should check the quality of our refined structure. Typically, we should check if the bond lengths, for example, in the PO4 tetrahedra are still realistic, and also the angles, if the tetrahedra are not very distorted. And I'm using a different software for that. It's called Vesta. We can download it for free from the website. I will give the link in the description below. And it runs also on all operating systems. We can get it for Windows, Mac OS, and Linux. And we have to export our refined structure as a ZIF file. So the file format we usually use to import structure files, we now use as an export format. And we can do it from the results menu, export ZIF files from list file. We choose this, which project, we only have one. And then we have to choose, do we want one single phase ZIF per phase? So as many ZIF files as we have phases, or do we want to write multiple phases into one ZIF file? Or if we had multiple projects, we could also combine all the structures in one large ZIF file. So usually we choose the first one. This is just additional information. We don't have to fill this in. So we just click yes or OK. And down here in the refinement protocol, it tells us where these files were saved. So we have one with the date, or no, that's the project name for hydroxyapatite, and another one for beta TCP, but we did not refine this, so we don't need it. And then in Vesta, we open this ZIF file. Here we have hydroxyapatite. This is our refined structure. And I want to define the tetrahedra and then draw it in polyhedral mode. So, and now if I click on one of the polyhedra down here, it will show me the bond length from the central atom, the P3, to the 4 vertices. And these should be very consistent. So if there was a strong variation among these bond lengths, the tetrahedron would be distorted. And that is chemically very unrealistic to have distorted polyhedra. So that would be a sign for an unstable refinement, probably due to limited data quality or due to over-refinement when we try to squeeze out too much information from our data. But this looks pretty consistent. That's a good sign. And we could also look at the angle variance, about 5 degrees variance. So this is quite okay for powder diffraction data. And in blue, these are the calcium atoms with the green fraction showing the strontium content. So this looks like an okay structure refinement. Such a full structure refinement as we've done it here is quite delicate. It's very easy to overprocess the data, and it's not recommended to just release all parameter at once without checking if there is actually a mismatch, because the more parameters we release, the more unstable and delicate the refinement will get. And in this case, we had to release pretty much all parameters, but it still looks okay. So it's always important to just double check and make sure that the refinement is still stable. So that was an example how I would refine a crystal structure. Usually I don't go as far as I did today with anisotropic displacement parameters and displacement parameters of oxygens and so on. I just fixed the most obvious mismatches, but just as an example, we went all the way to a full structure refinement. And I hope this was useful. If you stayed with me throughout the video, thanks for watching, and come back soon, and I will see you next time.